Thank you. Thank you very much to the organizers for putting this together. It's a real pleasure to be here and see so many friends. Quickly, before I go on, partner selection, that means that if you're nice to me, I'm nice to you. So it's easy to have stable multi-partner mutualisms with partner selection. What I'm going to talk about is some work where we're trying to figure out if we can do it without partner selection. But before I go on any further, I first want to say my thanks to Mark. Mark and I have never actually done research together, but we are academic siblings. So I was starting my PhD when Mark was starting his postdoc at the University of Washington. And we have continued to be in each other's orbit ever since, but never done research together, which means that every time I submit a grant proposal, I can write him down as a potential reviewer. So I think I owe him a lot of thanks. He's never actually told me. Yeah. Yeah. The other wonderful thing about Mark is, since we're both in Canada, we've had the opportunity to organize a lot of graduate student workshops. And every time I ask for help, Mark says yes. So having a good partner like that, a good mutualist like that, has been wonderful. And the other thing Mark has done for me, it's been mentioned a few times, what a wonderful community he created in Alberta. When I got back to Canada, it turns out he hadn't preceded me by much. He'd been in Utah longer. But as soon as I got back to Canada, I phoned up everybody I knew and said, I'm back. And Mark was one of them, and he immediately started inviting me up to Alberta to give talks and join in summer schools. And this is where I met Christina and Fritjof. And so I can't thank you enough for all of that. And then he started inviting me to Burr's workshops, and this is two of them. And one, so where's Mark? Here's Mark. And then here's Mark. This first one is where I met Jimmy, who you heard from earlier. And at the time, I already knew that I wanted a sabbatical in France. So, and he was apparently in France, so I got to know him. And then I saw him at a conference a few years later and said, by the way, I'm still coming to France. Is that okay? And he said, yeah, sure. And then, a few years later, can I still come? Yeah, sure. And we'd never worked together, but we worked together for a year and have been having a great time ever since. Got a few papers together. So thank you, Mark, for putting me in touch with some of my future collaborators. So what I'm talking about today is this work with Jimmy and our PhD student, Maria, who's now at doing a postdoc in Jerusalem. And Miranda is the biologist on the project. And I want to thank my research support, and I am grateful to live and work on the traditional unceded territory of the Syilx Okanagan Nation. Okay, multi-partner mutualisms. So this is a picture. We've got a whole lot of plants growing close together, and these plants share a number of mutualists. They share bees. We are familiar with bees, and if you haven't spent much time watching bees, I encourage you to do so. There's a lot more out there other than just the honeybee. Many, many different kinds of bees, and they are all sharing these plants. And so the plants are sharing the pollination services, and the bees are sharing the resources from the plants. And if you watch them, you'll find that many different bees will visit one plant at different times at the same time. How on earth could the plant tell which bee is doing what? So this is a case where the notion that you give me a lot, I give you a lot, isn't going to work very well. The mutualism that we can't see is underground here. There are fungi growing underground, and they are taking nutrients from the soil and giving them to the plant. So these fungi invade the plant roots. And they don't just invade one plant, they can invade several plants, and they do it in a very mixed up sort of way. They're not separated. And so once again, how on earth could the plant tell which fungus is giving it how much? So we would like to see if we can understand this system without partner selection. Here's just a quick overview of the biology. We have a plant. What the plant does is it can photosynthesize. That's a very special skill that fungi don't have. And so the plant can access carbon from the air, fix it, and then send it down into the roots, well, into the rest of the plant as well. But some of it goes into the roots where the fungi can access it. The fungi are growing in the soil. They invade the plant roots and build these exchange zones where the fungi give soil nutrients to the plant. We're just going to talk about phosphorus to keep life simple, but there are actually several things, and then take carbon from the plant. Now, what I've drawn here, and the fungi are better at this than the soil roots because they're so much finer. So what I've drawn here is I've drawn one fungus on this side and one fungus on that side, and this would be a split root design where there's no communication between the two, and so the plant can decide to give this bad mutualist not very much and this good mutualist lots. But in a real system, they're all mixed up, and there's no way, as far as the biologists know, that the plants could actually tell. So how do you get coexistence of a whole bunch of mutualists without partner selection? That's our first question. The second question is, once we've got a community of mutualists, can it be invaded by a less mutualistic fungus? And we'll look at a non-spatial system and a spatial system. And we're interested in the context where the invasive or the potentially invasive mutualist fungus is a commercial one. So when you go to the garden store and you buy your soil full of mycorrhiza, that's what you're buying. You're buying this commercial fungus, and you're introducing a biological organism into your garden, and what happens. And then finally, I'll give you a little teaser on the evolutionary work that we're doing now. Okay, so coexistence without partner selection. This is the model. Now, since it's a short talk, I'm not going to show you any of the mathematical derivations, so the citations are here if you're interested. I'll just show you the models and the results. So here's our model. It's a basic consumer resource type model. So we have a plant equation at the top and a fungus equation at the bottom. The plant grows because it gets phosphorus from the fungi, and there can be several, hence the sum term. The plant loses biomass because it has to give carbon to the fungi, and there are several. This is a sum term. The plant can grow without the fungi. So here's an intrinsic growth term, which we will often consider to be zero, and then add it in again later. And then there's this maintenance cost. And we've got a power n here. And the model works as long as n is larger than 1. Here's the fungal equation. So for each fungus, it gets carbon from the plant, so that's just the pair to that term. It gives phosphorus to the plant, so that's the pair to that term, and then there's a maintenance cost for the fungi as well. The important thing to notice here is the asymmetry. So notice that the amount of phosphorus given to the plant saturates with plant size. So the assumption here when we were doing it is that the plant is much bigger than the fungus, and the fungus can't keep giving as the plant grows. So for a small plant, the proportion received is proportional to the size of the plant and the fungus, but as the plant gets bigger, that saturates. The amount of carbon received from the plant, however, does not saturate. The fungus can take all at once as the plant grows. So this creates an asymmetry in the exchange of resources. And with that asymmetry, we are able to get coexistence of all of these mutualists on one plant. So this is time here. We're seeing the plant grow, and it eventually saturates, and then all 5 fungi, and so we've got one, sorry, I should have mentioned, this is back. So the key parameters are beta, so that's how generous the plant is. And alpha, that's how generous the fungus is. So in these results, we have 5 different fungi, so 5 different alpha. So, and it turns out plant 1 is fungus 1 is the most generous, and fungus 5 is the least generous, and then 1 plant. So we can get coexistence of all of these different mutualists on one plant. And what's happening is that these dark green relationships are the ones that we're modeling. Those are all the mutualisms. But what you have is you have indirect parasitism between the fungi. So the AMF1 here, so arbuscular mycorrhizal fungi is the full term, the short form is AMF. So AMF1 is the best mutualist. But that means that AMF3 and AMF2 parasitize AMF1. So AMF1 gives a lot to the plant, which means AMF2 and AMF3 get more. So we have this indirect parasitism getting set up. However, in this system, there's always room for another fungus. So we can have as many fungi coexisting on the one plant as we want. Okay, so what happens if there's an invader? So let's look at the non-spatial case. What we do then is we took the same model as before. I've collapsed terms into these F functions, functional forms, and we've added competition. So now we're saying that the fungi are competing between each other. And the competition is of this form. So that as the fungal biomass grows, then this competition becomes close to 1, and we have the amount of carbon supplied to the fungus goes down. They're competing amongst each other. So if you do that, and then we're thinking again about this wild community and a commercial invader. And the commercial fungi, they're raised in big facilities. They're not raised in the ground. When you want to grow things commercially, you want them to grow really quickly. You don't have time to wait for them to establish a nice mutualism with the plant. So you do everything in Petri type dishes. And so this commercial fungus is grown in a completely different environment from the wild fungi. So the commercial fungus is rewarded for reproducing really quickly, but not necessarily for being a good mutualist. So what happens when you introduce it to the wild community? There are basically these 4 outcomes. You can have, and this depends on how stiff the competition is. So that's the A parameter. Should have pointed that out. So this A parameter here. So if A is large, competition is less. If A is small, competition is greater. So if we vary the strength of competition, then we find that, and then we've also got the mutualist quality of the alien to think about. So we have these 4 cases. So we can have the alien species win, we can have the native community win, we can have coexistence, or we can have bistability, or one or the other ends up surviving. In the bistability case, what matters is your initial conditions. And then these are all steady state results. Okay, none of this is terribly surprising, but what we find out is that if the commercial fungus is a weak competitor, then it'll just integrate in the community, and we now have a more biodiverse community than we had to start with. But if that invasive fungus is a strong competitor, then either it wins or we have one or the other. It won't integrate into the community. And then the native community wins if it can compete strongly with the invader. Okay. So now if we add space to that same model, then we take the model we had before and now we add diffusion. We assume the plants don't move, just the fungi. And then these functions are the same that I showed you before. So in this case, we've got the same 4 outcomes I showed you before. Now they're in a line instead of in a grid, but we can have coexistence, the wild community wins, the inoculant wins, or this bistability case where we're not sure what's going to happen. The interesting thing here I want to point out is what's happening to the plant. So if you look behind the arrow, that's The behind the arrow is the steady state that's left after the fungus has invaded or not. In this case, we see that the plant does better because now we have a more biodiverse community. So we have all the wild fungi plus the commercial ones. So the plant actually does better. In this case, the wild community wins. And if it were, so out here, the plant wouldn't be doing as well. It does, because it just has the commercial fungus. So it does better when it has the wild ones, the wild community. So the basic result here in terms of the plant is that it does better. The more fungi there are, the better the plant does. The fungi, it depends on how they're competing amongst each other. The other result we found is that diversity is protective. So if we have, for example, just one wild fungus associated with the plant, and you bring in a commercial fungus, if it's a strong competitor, then it's going to displace the wild fungus. So this is the steady state behind the wave. The plant does really well for a while when both fungi are there, but at the end we have just the commercial fungus, and so the plant isn't doing as well. So this fungus is not as good a mutualist as the wild one, but a strong competitor, so it can get in. In this case, we have both coexisting, and so the plant actually does better. So again, if the commercial fungus is a weak competitor, that's better for the system. Now, if we have 2 AMF instead of 1, so suppose the initial community is 2 different fungi, and the commercial fungus is a strong competitor, that community of 2 will be able to keep the commercial fungus out. So this is a very small scale example of diversity, but the more diverse the natural community, the more likely they'll be able to keep the invader out. Again, if it's a weak competitor, it just integrates into the community. Okay, so far, what do we have? We have diversity of wild AMF protects against invasion, and then you want your commercial AMF to be a weak competitor if you don't want it displacing any of the wild community. So then the question is, all right, so we can get stable multi-partner mutualisms without partner selection, but can we get that system to evolve? So this is what we've started looking at. It's proving a little trickier than we originally thought. So when I submitted the title of my talk and said it was going to be all about evolution, I was being optimistic. But instead, I'll just show you a few results that we've had, mostly thanks to Jimmy. So if we take the same model I showed you before, but now we have diffusion in the trait alpha. We don't have diffusion in space. So this is the model with no space. But diffusion in the mutualist quality of the fungus. And then these terms A and B look like this, okay, where we have to integrate over all the different possible values of alpha in what's given to the plant and in what's given to the fungi. Okay, so if we look at that, what we find is that, so this is the mean value of the trait alpha. So it starts at a low value, increases, and then settles down to something which is most distinctly not 0. So 0 would be a total parasite. 1 would be a really good mutualist. It's low, but it's most distinctly not 0. And then if you look at the trait distribution at steady state, here it is. So we have a few really good mutualists and lots of parasites down here. So what we take from this is that it looks like in this system we can get a multi-partner mutualism to evolve, but it's not as mutualistic as we expect. So we know that in the real system, these fungi are very good mutualists most of the time. And so, so we have some work to do to try and understand the system better. But we can get this to evolve without partner selection. Okay, so future work is figuring out how to model the evolution process and see if we can figure out how these very beneficial mutualisms get set up in the real world. And that's all. Thank you.